Yeah, my board is not working well today, so I'm gonna. All right, today we finally begin to answer the question, when do things converge? Okay, so we're gonna introduce a concept called the radius of convergence to help us do that, and along the way you'll be reintroduced to something called the ratio test, which I think you might have a little bit of an acquaintance with from pre-calculus, depending on how that went for you. Okay. So that's like my intro. Like when we're good at finding the series representation for even a nasty function, we know how to take a bunch of derivatives if we really need to, and we can get the power series for that function if we need it, or we can use tricks to get it. But when does it actually converge? If it's geometric, we know the answer. But if it's not geometric, then we have to think hard here, a little bit harder. So for any series, there is a positive number r, for which one of these two things is true here, or that forms the dividing line between where it might converge and where it might diverge. And notice, by the way, that we're by the absolute value of x minus a, that should evoke in your mind distance from the center, right? Isn't that what that is? X minus a is absolute value, is the distance we are away from the center. So if that distance away from the center is greater than some number, then maybe it diverges. And if it's less than, if we're inside that, maybe it converges. And there are three different possibilities for what r could mean for our lives. We could have r is some number, like 5, in which case we mean that around the center, to the left 5, and to the right 5, it converges. So that's one possibility, is that this big capital R is a number, constant, in between 0 and infinity. It could be true that the number r is infinity, which means that the series converges everywhere. We might call that, we'll say what the letter r means in a second here. Or it could be that it's 0 and that it converges nowhere, except for exactly at the center. Have you noticed? Can you justify why? Every Taylor polynomial converges at the center. Why? Because the definition is f of a first, plus, and then some stuff. And at the center, of course, you get the function value no matter what. There's never a chance for a Taylor series to not converge at the center of the expansion if the function is defined. There.
How would one Taylor series function without defining it?
You could.
Because you couldn't define the first term.
Yeah. And furthermore, you can't, exactly. At any point along the way, if the derivative isn't defined, then you won't be able to write the Taylor series. Yeah. And this number r, I wanted to say it earlier, but here it is, finally. It's called the radius of convergence. And the radius is a good word for it because it's wherever we are, to the left and right of that place. It kind of forms the radius of the area of convergence. You might still not like the word radius of convergence because you're thinking well, where's the circle? But if you want to think about radius convergence in terms of circles, you'll just have to do calculus in higher dimensions to understand why radius of convergence is actually a really good word for it. Or with complex numbers, when we think about it, we might have a radius in the plane around the point where the series converges. So it does actually make really good sense when you do higher math. But right now, at least you understand radius convergence means to the left and right of where we are, by a distance r. David first.
Say r equals infinity.
Yeah, so I'm okay with that, though. We're going to let r be something that can be infinity. Yeah. Andrew, do you have the same question?
Yeah, the circle thing. Does this have anything to do with Lewis function?
Not directly. Are we going that? So those are the three things we're going to be looking for today. I mean, the three things that could happen. If we find r, then we're that's the goal. For any given series, can we figure out what capital R is? The radius of convergence. So the first one that's easy is geometric series. You already have this feeling already. We've already talked about this a little bit. That's why this should already feel a little familiar. For a geometric series, we know that it has to do with the common ratio, right? So we already answered this question. A geometric series has radius of convergence, little r, right? We should also say this. I think I've mentioned this in passing to some of you, but maybe not up front here. The second point, derivatives and integrals of those functions have the same radius of convergence as the original function. So do you remember doing that? We had something that wasn't geometric, but if you took the derivative of it, then it was geometric. And then afterward we integrated. Remember that whole trick? Or vice versa, you had something that if you took the integral, it would be geometric. As we do all that cool algebraic gymnastics, just keep in mind this fact that actually the radius of convergence doesn't change. Even if it's not geometric, if you take the integral or derivative it's geometric, then this same discussion applies. What about non-geometric series though? That's the big question. For that we have the ratio test. And the ratio test is basically just like, hey, it's not geometric, but let's pretend that it is. Okay, is basically what we're saying. You take your series, and up on top, we're going to put the expression for the n plus first term. And on the bottom, we're putting the nth term of the series. And then we're asking, what is the limit of this ratio as we go to infinity? And by this ratio, we mean the limit as n goes to infinity of the ratio of the next term to the current term. Just keep in mind that for a geometric series, what will this come out to? We don't even need the limit out front. It'll just come out to be r, right? Like for a geometric series. But what we're saying is if this comes out to a number, capital L, then that means that maybe out at infinity, this is acting geometric. The ratio between two terms approaches something. Yeah.
Theoretically, is that just saying that, like, if it's less than one in the term, just keep decreasing to a certain point at a time? Like, kind of what it's saying?
Say it one more time.
If L is less than 1, is that just saying how big the terms are relative to each other, decreasing every time, so that's why they're converging?
Yeah, it says that like if you do this ratio test and you get like the limit is 2 or something like that for certain values of x and stuff, maybe we'll say what that means. But if the limit is 2, then that means that it's acting like a divergent geometric series, right? Even though it's not, out at infinity, the ratio between one term and the next term is 2. Right? So even though it wasn't geometric, out at infinity, it's basically like you're multiplying by 2 each time. You get from one term to the next. So that's why this should look very familiar. Like I said, we're kind of like treating this as if it acts geometric. I'm glad these are on the same slide because we are thinking about this more broadly now. They're the same test. If we're on the boundary, then we don't know, right? Okay. But if we definitely know that if we're less than 1 or greater than 1, then we have something to talk about. Yeah, so what we're saying, and whether it acts geometric, this is also kind of us claiming that maybe it does. But if you evaluate this limit and it comes out to 2, then you've just shown that it acts geometric with common ratio 2 out of infinity, right? Because if you take this limit, the limit between, if you take the 100 first term and the 100th term and you divide, and you get something that's pretty much 2, then that means, and that's true also at the 1,000 first term and the 1,000th term. You get basically 2, then I think we can safely say that we have something that's acting geometric, right? I think an example will help. All right, let's find the radius of this power series. Notice that it is not geometric. Yes? Close, but not quite. There's an n up there. Do you see it? I was so excited, and then saw the n. All right, so we're going to compute this limit. That is the top. This thing right here is an. The whole thing. And an plus 1 is this whole thing with an n plus 1 instead of an n everywhere. Okay? So it's terrible looking, but here's how this is going to go. This is a division bar right here. Do you see that? This is a division bar right in the middle. So here is the n plus first term. Do you agree? All I did is plug in n plus 1 everywhere there's an n. And here is just the nth term. And now I do some fancy stuff, right? I'm all about like the reciprocal. Do you follow the first step? I've got more to show you here. But do you follow the first step? I just flipped this. So far so good? I mean, we're gonna do more algebra now. In fact, actually, I should be able to like not hold you back from doing algebra. There's like stuff that we wanna, yeah, I see. You wanna, Jack's back there. I'm excited about canceling things out, Mr. Chase. And I'm like, yes, good. We should all be excited about canceling things out. We see some things that have common factors. So, yeah. Do you agree that 3 to the n and 3 to the n plus 1 can be canceled out, leaving just a 3 in the denominator? Do you agree that x minus 5 to the n and x minus 5 to the n plus 1 can be canceled out, leaving an x minus 5 in the numerator? The n plus 1 and the n, I haven't decided what to do with those yet. But this next step, we can really do a lot to clean this up right away. Do you like that? Now the one thing I do notice is that n is the limit I'm taking, right? Let's get our variables straight here. N is the limit I'm taking. So with respect to n, x minus 5 has nothing to say about that. So I'm going to pull that out. It's still inside an absolute value, but I'm going to pull that out just to make it really clear what limit I'm taking. And the answer is I'm taking a limit of this expression right here, n plus 1 over 3n, as n goes to infinity. And that we can outsource to our pre-calculus friend, right? That's 1/3. All right, so what did we just do? We just computed L. We require that 1/3 be less than, 1/3 absolute value of x minus 5 be less than what? For this to converge, this is L. This whole thing needs to be less than 1, strictly less than 1. That is, we require that absolute value of x minus 5 is less than 3, and I think we have just found the radius of convergence. Right? Because by the radius of convergence, we mean a number, capital R, that the absolute value of x minus a is less than in order for it to converge. So the radius of convergence is 3. We'd say the center of our expansion is 5. We can actually name the places where this converges. It converges from 3 less than 5 and 3 greater than 5. But we're not going to yet come out and say the inequality. I know you're like dying to be like, yes, so therefore it converges between 2 and 8. But careful, if we want to write that inequality, I'd love to be able to write less than or equal to. And why is that something I still can't do? Well, because I don't know yet. It's inconclusive, right? When L is 1. I definitely know this converges though. I definitely know this converges up here if we're inside of this value, right? So I'll let you stare at this for a second here. Alon, go ahead, sorry. Why is this limit 1/3? I want you to think about this more, just for a second. You have infinity in the numerator too. Can someone answer? Yeah, how do we take this limit? What do you got? Yeah, you can think about end behavior from pre-calculus, Tyler. It's like a rational function with degree, the same numerator and denominator. Remember that? Or you can use L'Hopital's if you really want. But do you remember that from like pre-calculus? If you have like a quadratic over a quadratic, what's the horizontal asymptote? The ratio of the two coefficients on the highest degree term if they're the same degrees, right? So it's 1 divided by 3. Right? Okay, Dave? Well, I mean, for us, it's on the x-axis here. We're asking like what x values does this converge for? Yeah, and that's what I was saying. Is if we like include a discussion of complex numbers, actually use a circle, or if we go up into higher dimensional calculus, you could have like a ball of that radius, right? It's just the one-dimensional circle is not very interesting. It's like.
Oh, I know what it's constant.
Yeah, if it's not involved in the limit n then we can pull it out. Yeah. So yeah, let's go back to why do we like that last thing? Where is it here? Yeah, here. So we said if we can find something that converges if we can find a number A and a number R that makes this statement true, and we just did, the absolute value of x minus 5 is less than 3, and we didn't write it, but also x minus 5 absolute value is greater than 3 implies that it diverges, or yeah, 3, right? Then that's our R value. And if R is 1, if R is 0, if L comes out to be 1, then it's inconclusive. So we can't say anything about if we're at the boundary yet, but we do know about radius of convergence. We do definitely know inside it converges, inside of 3 and outside of 3 away from 5, it diverges for sure. Okay, let's do another one. My board is not working super well, so let's see if we can only point you in the right direction on this example. And I apologize for the people watching the video eventually. This is not going to be on it. Okay. Okay. So we're going to do the ratio test. Here we go. L is equal to the limit as n goes to infinity of, stack these things, n plus 1 factorial over n plus 1 to the 4th times x minus 3 to the n plus 1 all over this thing, right? N factorial over n to the 4th x minus 3 to the n.
What n equals doesn't matter. Like n equals 1 here.
Doesn't matter, right? All right, so now we start doing algebra. A whole bunch of algebra here. Sorry, absolute value of all this, right? You okay with my algebra here? So n plus 1 factorial and n factorial. Talk to me about that. Yeah, that's n plus 1 up top, right? By the way, we can pull out that x minus 3 now if we like. So we have n plus 1 times n to the 4th over n plus 1 to the 4th inside this limit. Tell me about that limit. Okay, so now I want to know when does this converge? Now I should say this is.
Please pardon the interruption for a brief announcement. Seniors, this is a reminder. If you are interested in speaking at graduation, you should attend the interest meeting taking place today at lunch in the main office conference room.
I should say it this way rather. When does this converge? Only when x is 3, right? It's the only time it converges. So therefore the radius of convergence is, what's the radius of convergence? 0. Okay, there's a little more to say, but I think we're doing very well, and I think you'll be able to do your homework. So your homework is this worksheet coming to you right now. Have a nice day,
Those of you who are running for office, yesterday's interested candidate meeting and today's lunch conference is also the Mr. White House Chair Sent Sanders this Friday at 8 p.m. All that will be available today at lunch on Main Street. With the purchase in place in order with Jason's please come to the office. Also, if you have to complete a grant project, come to room 229 during lunch. Will the following students please come to the main office? Gabby Cook, Stephanie Zhang.
Somehow think of the day if you can. I mean, we need to. I mean, you're supposed to make it up within a day of whenever you missed it, you know? That's just the 2 days, I mean. So you should make it up today for sure. I don't care whether you do it at lunch or at school or during lunch or class. Whatever you want. But it's today. I don't care when.